After the concept of the derivative, we will introduce the concept of the differential. It's very similar to the previous discussion, and the only difference is that we use 1 over 2 times a times t squared previously, but we use a common function at x equals ft here. Suppose the time starts from t0 after a short delay to t0 plus delta t. The vertical axis of t0 is ft0, and the vertical axis of t0 plus delta t is ft0 plus delta t. We also know the derivative of this function at t0, that is f prime t0, is the rate of change of this function at t0. It's a straight line. According to this straight line, if the horizontal axis is delta t, the vertical axis is delta t times f prime t0 equals delta x. In other words, if the derivative of the function at t0 or the rate of change can replace the nonlinear function, then when t changes delta t, the rate of the function's value can be expressed as delta t times the derivative of f at t0. When delta t tends to 0, delta x tends to the real change. It can be expressed as dx equals f prime t0 times dt. This is the limit condition when delta t tends to 0. Further, it can be expressed as the value of dx over dt at t equals t0 equals f prime t0. This formula means the value of the differential quotient, that is the differential x over the differential t at t equals t0 equals the derivative of ft at t0. So the derivative, the differential, and the differential quotient are closely connected. There's another discussion on this graph. If delta t is small enough that this error can be ignored, then the function can be expressed as ft0 plus delta t approximates to ft0 plus f prime t0 times delta t. When delta t tends to 0, the approximation tends to the equation. This formula will often appear in the following courses. You should remember and grasp it. With the concept of the differential and the integral, let's discuss calculus. The differential of t to the power of n is n times t to the power of n minus 1. The differential of sine t is cosine t. The differential of cosine t is minus sine t. The differential of e to the power of t is e to the power of t. We've discussed that it's a cumulative effect from a to a times t to 1 over 2 times a times t squared. It's a rate of change from 1 over 2 times a times t squared to a times t to a. So there's a close connection between the differential and the integral. Then we can use the equations on the left to calculate the integral of t to the power of n is 1 over 1 plus n times t to the power of n plus 1, because the differential of this function is t to the power of n. The differential can be expressed as this equation. If the upper and the lower limits of the integral are not given, then we should add a constant here. Because the differential of a constant is always 0, the existence of the constant doesn't influence the result of the differential. Similarly, the integral of sine t equals minus cosine t plus c, because the differential of cosine t equals minus sine t. The integral of cosine t equals sine t plus c, because the differential of sine t equals cosine t. The integral of e to the power of t equals e to the power of t plus c, because the differential of e to the power of t is still e to the power of t. Well, after knowing these conclusions, let's take an exercise which is a little complicated. You see, it's still about the relationship between the acceleration and the speed. Suppose the speed acceleration of an object is sine t. The time axis is from 0 to pi. We need to find the speed at t equals pi. Obviously, it equals the dashed area. We need to solve the integral of sine t from 0 to pi. The integral of sine t equals minus cosine t, so it equals minus cosine t, and the limits of the integral is from 0 to pi. Then it equals cosine 0 minus cosine pi equals 2. Then we know the speed of an object with such acceleration at t equals pi is 2. Here is a question for you. The acceleration of an object is like this. If the initial speed of it is 0 and the initial displacement of it is 0, then what's the displacement of it at t equals pi? Please think about it.